Good evening, dear all members. This is Clement, your chairman of Hong Kong branch. Today evening, I'm pleased to have our president of IMechE to deliver his presidential address. Now, the reason that behind it we want to set up that webinar, that is that president is supposed to be planning to pay the visit to our regions, Hong Kong, during this time. Unfortunately, this is due to the coronavirus 19. He is not able to make it. With that, I received his kindly letter to say we should do more often connecting. So in my reply, I suggesting presidents to deliver the speech, his presidential address to us in this time. So thank you, Professor Joe McGeough. He is our 134th president of IMechE. He was the seventh holder of Regius Chair and now the honorary professorial fellow at the School of Engineering, University Edinburgh. He holds a Bachelor of Science and PhD degree from Glasgow University and has held research appointments at the University of Leicester, Queensland, Strathclyde, and Aberdeen. Professor McGeough has both academic and industrial experience, and he's also held a Royal Society SERC industrial fellowship to develop unconventional electrochemical machinery (D.T.N) method for applications in the aircraft engines, car, offshore, and medical device industry. At Edinburgh, he's developed research collaborations with clinicians at the Royal Infirmary to investigate the effect of age on mechanical properties of human bones, the significance and the cause of back pain. He has published widely. Before I pass it to Professor Joe, and there will be the Q&A section after his speech. So if you can type in the Q&A questions so that we can pick up to answer your questions. Without further ado, can I pass it to Professor Joe McGeough, please?
Okay. Clement, thank you very much indeed for that very kind introduction. And good evening to our members in Hong Kong. As Clement said, I'm Joe McGeough. Last May, I became the 134th president of the Institution of Mechanical Engineers. I live in Edinburgh in Scotland, and I had planned to come in March of this year in order to present in person the George Stephenson, the Presidential Lecture. There was a Scottish poet, Robert Burns, who wrote 200 years ago, "The best laid plans of mice and men often go astray." I'm sure Robert Burns wasn't thinking of the coronavirus at the time, but that put paid to the chances of me coming when British Airways cancelled both my incoming flight and my outgoing flight. Since March, I've been in lockdown in my home here in Edinburgh, and I'm presenting the presidential lecture here from my house. Since March, the IMechE, we've been running the IMechE by teams, and just about 3 or 4 weeks ago, I asked the events team, would it be possible to present the presidential address by virtual means? And I was bearing in mind when my friend and colleague from the IMechE, Otto Poon, came into the IMechE in February, and I told him about my plans to come to Hong Kong. And in some ways, in many ways, it was a great regret to me that I couldn't come in person. And I hope this is plan B. We're actually presenting it and finding that we can actually do these things by virtual means. In February or March last year, I was asked what was going to be my presidential lecture. And that posed immediately a number of questions. He's supposed to give some kind of experience of what he's done in his working life. I wondered, the word engineer means inventiveness. Could it include some form of invention? How do we as engineers tackle problems for which there is no known solution, finding an engineering solution? How do you deal with setbacks and failures? And a former president of the institution, Bernard Crossland, used to go around the world talking about engineering failures. How do you deal with failure, not just in engineering, but in your personal life? How do you inspire young people to follow a career in science and engineering? In my case, it's been a long time since there was a president who came from Edinburgh. How can I give it an Edinburgh-based theme? How do you make a presidential lecture attractive to a general audience, since we all come from different backgrounds and disciplines? So the task that I had was, how could I put that all together? And I hope that in the course of this lecture, we will see how I've tried to answer these questions that are put to a president every year. So on to the first slide, Emma. Here we are. George Stephenson was the very first president of the Institution of Mechanical Engineers. And way back in the 19th century, they built a steam locomotive called the Rocket, driven by steam. And one of my first duties last year, when I became president, I was invited back to my university where I graduated, Glasgow University in Scotland, that was celebrating the 200th anniversary of the death of James Watt. And it's James Watt's steam, an application of steam, that actually drove the rocket. On to the next slide, Emma. Here's the second president of the institution, Robert Stephenson. And here's where this connection with Edinburgh and Edinburgh University begins. George was preparing his son Robert to take over the family business. They knew that steam would drive their locomotives, but they realized that they had to understand more about the properties of steam. And George, the first president, sent Robert Stephenson to Edinburgh University to take lectures in physics, mathematics, chemistry, and also geology, since they were building the railroads themselves. But those were the lectures that Robert Stephenson took here in Edinburgh. And it must have inspired the university to go about applying to the Queen of the day, Queen Victoria, to establish what became known as the Regius Chair of Engineering. The two Stephensons realized that they could get the engineering and technology back at their own works. But the science and mathematics that Robert learnt in Edinburgh became known as what we know as STEM: science, technology, engineering, and mathematics. Next slide, Emma. Here we've got Edinburgh Castle, this landmark that probably appears in every postcard that any tourist sends here from Edinburgh. And it's just probably less than a mile, just a few 100 metres away from Edinburgh Castle is the home of where the title of this, Theo Williamson, this Edinburgh man, lived. Next slide. Here we are. It's now a guest house called the Town House. And that's where Theo Williamson lived. His father had a car hire business. His father was also a great do-it-yourself man. And he equipped, in the 1920s and 1930s, equipped every room in the house with an anthracite stove. And Williamson said many years later that it was the best heated house in Edinburgh. Williamson, when he was 5, 6 or 7, became very ill. He developed tuberculosis, and his parents worried for his life. His father also was experimenting with radio. Those were the early days of radio. And while Williamson lay in bed recovering from TB, he would start to read these magazines about wireless, and also a magazine, Popular Science, and it really in some ways inspired him. These were the first hallmarks that this man had a scientific interest. He wasn't interested in sport, but I think it was the TB left him physically weakened for many years. Next slide. Here's a former president of the Institution of Mechanical Engineers, whom I saw just a few months ago at Birdcage Walk in London. Brian Kent. And he was presenting a certificate to the lady who now owns the house concerning some of the achievements that Williamson carried out. The man on the right-hand side was James Holmes. He worked with Williamson, and he also was a member of the IMechE. Next slide. Williamson went to this school in Edinburgh called George Heriot's. And you see the building there on the right. It was built by, the funds for it came from the goldsmith to King James VI of Scotland and the First of England. And he left money for a school to be built so that poor young people in Edinburgh could receive education. On the left-hand side of the screen there shows 2 prizes that Williamson won in the later years of his time at school. One was for a radio-controlled boat. And bear in mind, this is the 1930s, when radio really was only becoming known. And also he won a prize for building a lathe that could turn record discs in the early days of the gramophone industry in the UK. Next slide. In preparing for this lecture, I got in touch with the archivist for Williamson School, and look at these marks. This was just taking what were called Scottish Highers, the equivalent A-levels or GCSEs. But look at the marks. There's nothing at all surprising or enterprising about these marks. There are roughly between 30 and 40 pupils in the school. Look at the marks. German, chemistry, probably about average, physics, average, mathematics, average, English, average, and you needed English to go to a Scottish university. And the only thing that was outstanding was Williamson's achievements in handicrafts, of all things. First place for handicrafts. And that wouldn't have got him into any university. But the physics and the chemistry and the mathematics and English were necessary, as indeed was a foreign language. In this case, it was German. Next slide. At that time, there were only 4 universities in Scotland, and his local university was Edinburgh University, and he was able to walk or take the tram or take the bus, and that shows him the matriculation document that let Williamson go to university, and he chose to go there and study engineering. Next slide. Here was and is the main entrance to engineering at the University of Edinburgh. The building on the right-hand side there was called the Sanderson Building. They were textile manufacturers, and they gave funds to the university to build an engineering building. It was state-of-the-art, great laboratories. It was opened by a Prime Minister called Ramsay MacDonald in 1932. And you can just imagine Williamson's excitement in going up those steps to start his university education in his first year. Next slide. It was called a Bachelor of Science degree in engineering. The university had established a science and engineering site called King's Buildings after the king of the day. And there, Williamson, in his first year, was able to study mechanical, civil, engineering, and also mathematics. The university had a close relationship with what was then Heriot-Watt College, now a university in its own right. And because it lacked the staff, Williamson went to Heriot-Watt College, where he got lectures in electrical engineering from a man called Professor Say. Say had never published a research paper in his life, but he was a very good lecturer. And he inspired, just by his good teaching, and there's a lesson for us in academia, he inspired Williamson by his lectures. When I came to Edinburgh University, first of all, I found that Professor Say, then into his 90s, lived just down the street from where I live. And I went down to meet Professor Say for the first time. Next slide, please, Emma. Electrical engineering lectures were fine. So was the mechanical and civil engineering. But Williamson had a problem, and the problem was mathematics. And for four occasions, he sat the mathematics exam. In May, the main degrees. September, they were called resits. And because it was wartime, and the need to push engineering graduates out where they could be useful, he was allowed to carry the mathematics into the second year of his engineering course. And he failed the mathematics again in May and again in September. Under university regulations, that meant that he was not allowed to carry his course further, and he had to discontinue his studies in engineering. He was called up for military service. He had a medical check, and they found he still had a shadow in his lung caused by the tuberculosis from his early days. And he also failed his medical. He was a total failure. And you can imagine the derision and the resentment of other families where their sons were away fighting, that this man had failed everything that he did. What Williamson didn't know at the time, and it was probably no consolation to him when he found out later on, was the next slide shows Robert Louis Stevenson. Robert Louis Stevenson came and studied engineering at the University of Edinburgh too. And he had to discontinue his course as well. Robert Louis Stevenson had come from a family that built lighthouses around the coast of the UK. And the father wanted Robert Louis Stevenson to enter the family business. And Williamson found that he had no taste at all for engineering. Incidentally, his grandparents lived in the district of Edinburgh, Collinton, where I live. And there's a statue to Robert Louis Stevenson that used to come out there for his summer holidays to meet his father, who was called David Balfour. And that was the name that Williamson introduced into one of his books, Kidnapped. And of course, he's better known for writing Treasure Island. Failure in engineering at Edinburgh, Robert Louis Stevenson. Here's another failure. Next slide. Charles Darwin came and studied medicine at the University of Edinburgh. And he had to discontinue his studies as well. He didn't like medicine. And of course, he went on to achieve greater heights elsewhere, writing The Origin of the Species. With some trepidation, the head of the University of Edinburgh came when I did the presidential lecture here at the start of March. And when I brought these 2 points, the principal of the university said to me, yes, he said, I knew about that. I knew about Charles Darwin. I didn't know about Robert Louis Stevenson. He said Darwin went on to study theology as well at the Cambridge University before going on to achieve world renown. So there's a marketing strategy there. I don't really know what it is, but it's not being said, come to our university, study, we'll fail you, and then you're made forevermore. On to the next slide, Emma. Williamson had to do something, and he applied now to the Scientific Civil Service in the UK, because radar was starting in those days, and he thought he could make a contribution there. C.P. Snow was the government recruitment officer for their science laboratories. Later on, he became known as an author, a writer of academic political books. Williamson was interviewed by C.P. Snow, and Snow said to him, look, I can smell a research engineer or scientist a mile away, and you're not one of them. And he turned down Williamson's application to join the Wartime Scientific Service. Yet another failure, yet another rejection. Next slide, Emma. Instead, he was drafted to the MO Marconi Osram Valve Company in London. And you can imagine this is wartime, staying in drafty cold digs, ration books for food, tripping in every day to this dodging bombs, and his task there was the most mundane, tedious of tasks. And that was to test valves for aircraft and for the military. And the job was to put a valve into a machine. If it lit up, the valve worked. If it didn't work, if it didn't light up, it was put to one side. And Williamson's job was to test food. That was his job through the day. It was the only thing that people considered him good for. Next slide, Emma. He had a good boss, Graham Woodville. And some years ago, at the age of 90, I went to see him. And he said, yes, I remembered Williamson. He really was totally frustrated. He said, Graham Woodville said, I was a radio man. I said, that's why I was doing it. He said, we 4 or 5 people. That was all that we're doing, including Will. And he said, but look, he gave me this letter. And he said, this showed how much GEC, they were the people who were manufacturing the valves for the Royal Air Force. And so that was a testimony to how fastidious and conscientious Williamson was. He said, but I realised he was frustrated. And I said, he'd been telling me about his father building radios, And Woodville said, and he also told me that he had his own ideas. Williamson had his own ideas about how to build an amplifier for gramophone records to improve the quality of the sound. And Woodville said, well, I'll tell you what, if we've got 400 valves to test one day, you test them, do the job properly, but after that, you've got to stay here until it's time to go home. And you use your spare time to try to design your amplifier for sound reproduction. Next slide. And that's what Williamson did in his spare time when he finished testing the valves. He designed an amplifier, and the quality of sound that came from it was tenfold clearer than what was available at the time. Because it was wartime, he couldn't publish it, but when the war was over, he published it in a magazine called Wireless World that his father had read in the house in Edinburgh. And incidentally, a magazine that my father also used to read when I was a child too. Next slide. And there we are, published in Wireless World, coupled with a lightweight pickup. It was, the clarity of sound was far better than anything that had ever been achieved before. Because it was published, the design was free. And that amplifier was designed by enthusiasts virtually in every country in the world. Many years later, as we'll come on to the next slide, when Williamson went about other business, when he worked for Ferranti, he would go into factories and people say he would hand over his business card, D.T.N. Williamson, and they would say, are you the D.T.N. Williamson who designed the amplifier? And Williamson, quite a modest man, would say, yes, I am. And they would say, gosh, it was fantastic. And the doors were opened. Williamson could do no wrong. On again, Emma, next slide. The managing director of Ferranti was a man called John Tootle. Tootle had trained as an engineering apprentice, but he found his interests were much more in terms of accounting and finance and management, and he transferred into that side of the business of Ferranti. But he could speak to engineers and knew how they thought. Bear in mind, this was now the Cold War and into the 1950s. Ferranti had a huge contract from the Ministry of Defence in the UK to build radar sets and radar guides for the Ministry of Defence for the Royal Air Force. And Tootle had a big problem in his hands. The machine tools that he was using, the milling machines and the lathes, turning machines, were ill-equipped, were too old-fashioned to turn out parts that would produce the consistency and the quality of the parts that were needed for waveguides. He had a big problem in his hands, with the big contract. The Ministry of Defence were leaning on him, and he knew that he couldn't deliver. For some reason that is still unknown to this very day, Tootle said for Williamson, and he said, Williamson, I've got a problem here, and he told him what the problem was. I want you to go away and get 2 or 3 of your young friends and in the company and try to come up with some solution to the problem. How do you deal, members of the Hong Kong IMechE, if your boss comes to you and throws a problem at you for which there is no necessary, not always solution. Next slide. Here was Williamson, just like the two first presidents of the IMechE, putting together science, technology, engineering, and mathematics. They realized that most of the parts that made up the radar waveguides could be broken into parts of straight lines, circles, ellipses, and parabolae, curved. As you listen into this webinar, why don't you just have a quick look round the room, and you'll notice that most parts in your room are made up of straight lines, curves, etc. Ferranti, Williamson and Ferranti, they worked out, could they use a computer program to generate these shapes, to draw them? And bear in mind, this was the early days of computers. One of his colleagues was called Donald Walker, that's a good Scottish name as well, and he worked out a mathematical tool that would let a computer produce those shapes. It was called the Digital Differential Analyzer. Here in the 21st century, we think digital, Industry 4.0, the digitization century is a new thing. But it's certainly not. There was Williamson, last century, facing up to a digital solution to an engineering problem. And they wrote a computer program, and they generated those shapes. And then they said, could we transfer the data to make them to get a milling machine to make the shapes? And that was the big step forward for Ferranti. And that became the beginning of Ferranti computer-aided machining, computer-aided milling. Ferranti took out the patents, unlike the design in his amplifier. And in conjunction with an aircraft company, they used the Ferranti computer-aided milling machines to make parts for the Trident aircraft and for the aircraft carrier dump jets, the Sea Harrier. And the last one, Ferranti, Williamson said later, that was probably one of his proudest moments at Ferranti. He said that was arguably the best engineering that he'd ever done. Science, technology, engineering, and mathematics. The science and the mathematics they did together. Ferranti did the technology, and they did engineering. And here's a man that couldn't pass a mathematics exam. Next slide. Computer-aided manufacturing. And that is one of the hallmarks to this very day of Ferranti. Computer-aided manufacturing. Computer-aided CAM. Next slide. Here's an interesting twist. Computers in those days were virtually unknown. Ferranti had a big branch in Manchester, and they'd got into collaboration with Manchester University. And the man, Alan Turing, who had broken the Nazi encoding machine, the Enigma machine, after the war, had come to Manchester University, and in conjunction with Professor Williams, Turing built computers that could be used in industry. And those computers were adopted by Ferranti. And that's the computer that Williamson used to drive his machining operations. Thanks to Alan Turing. And some of you have probably seen the movie, The Imitation Game, that featured Alan Turing and his work with the Enigma machine. Next slide. Here we are. There we are. using computers. And look at the waveguide in the bottom made of aluminium. And look at what we're saying just above. There's the sketch. Look at the straight lines, the curves. That was the big breakthrough that the Ferranti team with Williamson put together. Only about 4 or 5 of them, including James Holmes, the man that I showed you in the slide at the beginning with Brian Kent, the then president. Next slide. They weren't finished yet. They took their ideas and their work back to Tutel. And he threw another question at them. Okay, that's fine, but I want to sell our customers true data with the Ferranti milling machine system. I want you to go back and design and build an inspection machine that we can rely on. And they went to the National Physical Laboratory just outside London, Teddington in Middlesex. And in conjunction with the team there, they used a photographic medicine called using differential gratings in order to design an inspection machine. And this was totally unheralded as well. Patents were taken out, and those inspection machines are still being used and sold by Ferranti to this and its successor to this very day. All due to Williamson. Science, technology, engineering, and mathematics, yet again. Next slide, please, Emma. One good thing about Tutel and the management was that he would let his young staff go and talk at meetings. And Williamson was able to go and talk about the Ferranti computer machines at a conference called the Automatic Factory that was run by a sister body called the Institution of Production Engineers down in Margate in the south coast of England. Incidentally, the Institution of Production Engineers had many discussions of joining up with the IMechE, and one of my personal regrets is that actually never had it, and they went to another engineering institution instead. What Williamson didn't know was that there was somebody sitting in the audience who had come from London in order to listen to what Williamson was saying. This man had already been doing some business with Ferranti, but this man on the next slide, Emma, well, I beg your pardon, let me just introduce this. By this time, Williamson was married. A lady called Alexa, a very pretty lady. She was working in the laboratory where Williamson was working. She had graduated in business studies from Edinburgh University. They fell in love. All work and no play makes a dull boy. But they fell in love and they get married. And there is the first slide in this whole series so far of Williamson. You see him there. He was quite a tall man. His parents on one side and Alexa's parents on the other. And Alexa told me many years later that they came back to Edinburgh at one stage and they went to see Professor Say. Professor Say told her that even in those days, he realized that her husband was a genius to me. Next slide, please, Emma. The man that I was talking about was Des Molins. You listen to what he had to say. Molins was a family-run business in London. They had problems in that they made cigarette machines. They didn't make cigarettes, but they made machines to make cigarettes, which they sold all around the world. And Molins realized that they were falling behind their competitors in that they were not using the latest technology. He approached Tootle, said they wondered whether they could approach that young staff member who had spoken so well at the meeting in Margate to the Institution of Production Engineers. Tootle gave permission, and they approached Williamson. Bear in mind, by this time he was married, they had 3 children. They had discussions. They offered him a salary that was 4 times that of the British Prime Minister. They offered him a salary that was 4 times the salary at Ferranti. Williamson agonised over it, couldn't make up their minds, happy with their family in Edinburgh, and eventually he went and saw Tootle himself. Tootle said, well, you know, in no way can we match this salary, but I think you should accept it. And Tootle must have realised that this man had more to him. This was a man who was a failure, had no qualifications at all. And eventually they decided, and they closed their eyes and jumped, and off they went to London to work for Molins, where he became Director of Research and Development and also a seat in the board. And what Williamson did was he worked on introducing computers there to perform the entire industrial operation, making machines, and also introducing accounting through computing in many days and just-in-time technology. And the next slide, please, Emma, shows what became known as Molins System 24. And there's a model on the right-hand side. A totally new concept. Flexible manufacturing systems. Manufacturing controlled by computers, running round the clock. It could take account of changes at the last moment, breakdowns, queuing, timing. And robots being introduced to transfer parts from one machine to another. Totally revolutionary. Never done before. Molins patented the whole system and it became known as Molins System 24. The model on the right-hand side was built under Williamson's direction by a design engineer, because it not only wanted to take this out where people couldn't come in to the factory to try and sell the system to those that were interested. One of the industries that really was interested was in the next slide. The car industry. And they adopted readily Williamson's flexible manufacturing systems. All patented and made a fortune for Molins. Next slide. And that's why this inaugural lecture was called How Theo Williamson Changed the Sound of Music. And these were, you've seen the sound of music from the amplifier. These, I've quoted Williamson's own words when they were building System 24. He felt, in hindsight, that he was like a conductor. He had a team of about 100 people working for him. Everybody played their part, just like everybody in an orchestra. And he was the conductor, conducting it. And like the best compositions from music, he said that the eloquence of that creation has never really been surpassed. And here was a message to us. He also said, in his case, the car industry adopted flexible manufacturing. The Molins had many discussions with IBM. They wanted to see their computer systems introduced. And that little note there, he spoke about this at a conference in Manchester University, where the Turing computer had come from. In big engineering, if you want to succeed, you need the cooperation of the big boys, the IBMs and Rolls-Royces, for it to work. Next slide, please. Williamson was invited by the Institution of Mechanical Engineers to come and give a talk about these achievements. And it became the James Clayton Lecture, and those members of the IMechE in Hong Kong, some of you who have been to London, will have attended the James Clayton Lecture. It was delivered by Williamson at 1 Birdcage Walk, and there's the building outside. After the lecture, he was told by the then president of the institution that they would like to award him a prize that was given to members of the IMechE who had made distinguished achievements in mechanical engineering. And William said, well, he said, I'm very sorry, but I don't have any, I'm not a member of the IMechE because I don't have any qualifications. So I couldn't become a member of the IMechE. And that was the end of it. But sitting in the audience was somebody called Dr. Bob Fielden, who was a member of the IMechE, who was also a fellow of the Royal Society of London, which is the most distinguished body for mainly scientists. People like Stephen Hawking was a fellow of the Royal Society of London, Isaac Newton. Very few engineers have been elected to it. But Fielden listened to what Williamson had said that night, and he went and saw the president of the Royal Society, a man called Lord Blackett, a Nobel Prize winner, and explained to Blackett what he'd heard Williamson say. And Blackett said, well, why don't you go put an appointment with Williamson and go to Molins and see it for yourself. And that's what Fielden did. And he made an appointment, went up to Molins, which was in London, of course, spoke to Williamson. Williamson gave him a tour of the factory, saw flexible manufacturing for itself, and Fielden came back to see the president of the Royal Society and said, what this man is doing is truly revolutionary and remarkable. And Blackett said, do you think we could propose him for fellowship with the Royal Society? And Fielden said, I think that would be most appropriate. And Williamson was duly, next slide, Emma, was duly elected a fellow of the Royal Society in the same very year, joining this august body. And that was a game changer for Williamson. And Mrs. Williamson said to me when I met her that that recognition had made up for the bitterness and the disappointment that he'd had in his earlier days. He was now a fellow of the Royal Society of London. Williamson now found himself being invited to join many bodies. Next slide. One was the National Economic Development Organization. He was sitting with senior industrialists, trade unionists, trying to come to some strategy as to what the future of manufacturing, mechanical engineering in particular, in the UK, how it was going. And he was presented by this slide by the civil servants, which showed the trade balance for the UK, for mechanical engineering. Now, bear in mind, this is between 1970 and 1980, before oil had been discovered in the North Sea. But look at the drastic fall in the trade balance, the difference between exports and imports. The imports were overtaking exports. And he really was worried at what he saw. In parallel, Williamson now found himself being invited to join the body that funds research in our universities, then called the Science and Engineering Research Council. And the next slide, Emma. He was invited to join the board for engineering, and he was given particular responsibility for manufacturing engineering. He advocated that the Research Council should draw on the expertise, the bright ideas in universities, and see them transferred into industry, in particular manufacturing engineering. Next slide, Emma. And he put through something that became known as the Teaching Company Scheme. The symbolism of the pigeons was that they were carrying a message. The top hats is a very kind of British thing, but the message was we have got to use their expertise and transfer their bright ideas into industry for that trade balance to be changed. Start-up companies and spin-off companies to follow. That was bitterly opposed by some of the leading academics in engineering in the UK at the time. In particular, one very eminent professor of mechanical engineering that I knew at the time wanted it recorded that he totally opposed this scheme and would not have any part in it as far as his university was concerned. Yet, that has been the most successful university industry scheme that ever came out from the Research Council. Next slide, please, Emma. The Teaching Company Scheme. It strengthens the competitiveness between industry. It lets academics work with industry. It stimulates research and development. And look at the satisfaction level. 75% of industry and 70%. So good satisfaction levels. And look at the large number that go to small to medium-sized enterprises. That is roughly people under 50%, under 500 employees. I had one such scheme. Next slide. I was using water jet, a powerful jet of water, and I worked with a firm in Newcastle-upon-Tyne where the two Stevenston had done their work. And my project was that I was using highly powerful jets of water to decommission the oil rigs that were now 30 years old in the North Sea, using computer-aided engineering to do so. By that time, I was also working with the academics, with the clinicians in the hospital here in Edinburgh, as Clement said earlier on. And we're working on new methods of cutting for medicine. And I did some experiments in the company when we'd finished our work for the day. Could it cut bone? Could it cut tissue? And when I come back up to Edinburgh, we carried out 4 more experiments, and we developed new technology that is now used in practice in medicine. Next slide, Emma. For cutting bone and tissue. And that shows you how you can take technology in one complete area and transfer that over into an industry. It's also been used for cataract removal, and I understand it's also now being used in neurosurgery, water jets. How to transfer really macro engineering to a micro nano engineering state. Next slide, please, Emma. When I wasn't doing that, I was mainly working for the aircraft engine industry in the UK, doing things like cutting fine holes for aircraft turbine blades by electrochemical machining, using incidentally not steam but electricity. So another of my heroes has been Michael Faraday. Turbine blades, cooling holes for aircraft jet engines, turbine blades. And related technology, next slide, Emma, called spark erosion. Interested, spark erosion was developed in Russia, in Moscow, by the Lazarenkos when their country were suffering a severe lack of industrial diamonds during wartime. And that's what I'm working on. But back at the Research Council, next slide, Emma. Williamson was faced with yet another problem. He was told that those working in the dye and mould industry were suffering a severe lack of skilled mould makers, and more importantly, those concerned with finishing the dyes and moulds. And those are some examples at the bottom of there. The mobile phone, the plastic covering for that, the CD discs, the wheelie bins, and up in the top left shows an example of a part. And I was given a task that Williamson said, look, we've got to find out where in our universities in the UK is the expertise in electrical methods of machining, electrochemical machining and electrodischarge machining. And he set up a coordinated programme of research in UK universities where the lack of traditional methods of making dyes and moulds and finishing them could be replaced by modern technology. Next slide, please, Emma. There we are. And that was the sequence. Making EDM, finishing by electrochemical machining, combining the two processes. It was a coordinated programme of research, and the partners were myself, Birmingham, then Warwick, and Cranfield universities. And we had a senior industrialist who came once a week to each of those universities, and then in the fourth week, he would report back to the engineering board, reporting our progress. We were not allowed to divert from the programme. We had to transfer the technology. And the industrial fellowship that Clement referred to earlier on in the discussion, that's how that came about. And I had to go back and ask the university if I could hold a special fellowship funded by the Royal Society and the Research Council that would allow the technology, my work, to go on over into industry. And that was due to Williamson. I'd never met him before, but the industrialist who came up, he told me about this remarkable man, Williamson, who was driving this programme and driving the teaching company scheme. At this stage, Williamson became ill, and he was off work for some months, and again his life was threatened. During that time, the Mullins brothers decided to sell their shares in the company. They sold it to a cigarette company called Wills, who had a big factory in Wills. And when Wills sent in the accountants to look at the books, they discovered that Mullins were expending a huge amount on the next stage of research and development for computer technology. And they stopped the programme while Williamson was off ill. When Williamson returned back from home, he found the whole programme had stopped. And he had senior engineers coming into his office, crying their eyes out that the next stage of computer-aided engineering had been stopped by accountants simply looking at the books and not seeing the bigger picture. He stayed for about a year or 2 years, and then he left. Next slide. He joined Rank Xerox. He became the European Group Director for Research. And Rank Xerox, but again, another big company. Back to Williamson's philosophy. If you want to see new technology going through, you've got to have the big boys behind you. Next slide, please, Emma. And what he worked on there was what became known as the fax machine and colour printing. Now look at that little note at the bottom there. I did a very early version of the presidential lecture to the IMechE in Inverness in the north of Scotland. And somebody told me, he said, that's only strictly true because a man called Alistair Bain here, we think, also invented the fax machine. And I came back and there were patents in the 19th century, the early days of photography and the telephone, that a man called Alistair Bain had patented. So there were 2 credits to Williamson and Alistair Bain. Williamson worked for Rank Xerox for 2 or 3 years, and then he decided that he had had enough. And the principal of the University of Edinburgh told me, I mentioned this, he said, well, maybe he just felt he'd done enough. And Alexa and he, next slide, retired to Italy. I went to a university, I'd never met him by this stage, and at the time of the D.T.N program using electrochemical and electrodischarge machining, I got his address and I went to a conference and I wrote to him and I went to visit him at his home in Italy. The daughter, I gather, had set up a ballet company in Italy, and that's why they'd gone to live near to her. He still worked for his son, who was running an engineering business back in the UK. But Alexa told me that he had designed the house, and the ceiling of the house was acoustically perfect, that it would receive sound that really was unsurpassed. Next slide, please. Back in Edinburgh, the 2 universities realised that a huge error of judgment had been made. And first of all, Heriot-Watt University, where he'd received those excellent lectures in engineering, electrical engineering from Professor C, granted him a degree, an honorary degree. And then the University of Edinburgh, next slide please, Emma, followed on. And they too awarded him an honorary Doctor of Science. And there's Williamson in the front row there, second from the left, say, receiving his diploma. And the right-hand side is the university principal, the head of the university, Professor Sir John Burnett. And he had encouraged me to take the fellowship, go part-time for a while, and get the technology through into industry. Other principals of the major seniors in the university, one on the left-hand side on the bottom was called the student rector. He was the student, he was a sports commentator. He represented the students at the university court, the governing body. But there was, first of all, the university finally gave him the degree that he probably should have got in the first instance. Another interest of mine is that I like to see people being encouraged to do engineering. And after I came to Edinburgh, I was invited to visit a big company called Brown Brothers. They're now part of Rolls-Royce, by the way, and they made ship stabilizers. And they said, what can we do for you at the University of Edinburgh? I said, well, how about you funding a series of sponsored lectures where I can invite some of the big names in engineering to come and talk to our students, and even schools pupils. Get schools pupils in through the door, where a university is not an ivory tower, but you see it actually exists with real people. And they did that, and for something like 6 or 7 years, I was able to invite chairs of big companies, the chair of British Rail, the chair of Vickers, Jackie Stewart, the racing driver, and also William Walker, who was the chairman of Brown Brothers. He gave one of the very first lectures to tell them how he had become chairman of a big company, putting fire into their bellies. And after it, he said, look, I'm going to give you a standing order. For £50, that is not an annual sum. I said, just do with it what you want. And I tried it out. Somebody once said, a philosopher once said, give me the child between 5 and 8, and I will give you the man, I'll give you the person. And that's the time when you want to introduce young people to science and engineering. And I tried it out in 1 or 2 primary schools, and then I took the problem to the junior headmaster at the school that Williamson had studied at, George Heriot's, and explained what I wanted to do to the junior headmaster. And between him and me, we set up a competition where primary 7, that's ages 10, 11, they would do a little project about an engineer. James Watt, Dunlop, pneumatic tyres, and the first one that they did was for Williamson. I went and gave them a little talk about Williamson. And that's probably the most difficult thing you can do, is how can you tell young people about engineering and make it interesting and attractive to them? And the task was that they would write an essay, maybe just about a page, 200 words about Williamson had done, and then they would build a model of his work. And the next slide, please. And there we are. And that's what primary 7 pupils at George Heriot School did. Look at the thing on the right-hand side there. There we are. There we are. That is their idea of computer-aided manufacturing. What their idea of a computer, the white box represents the computer. The black box is the computer-aided bit, and the thing that comes down the chute is the part that's been made. On the left-hand side was their idea of flexible manufacturing systems made out of Lego, of putting parts together using flexible manufacturing systems. And the bit over the middle is the Williamson amplifier. You can see the loudspeaker at the bottom and the speakers themselves. It just shows you, age 10, 11, maybe 12, how creative young people can be at that stage. So the £50 was transferred over to his old school. Everybody got a prize. £20 to the first prize, 10 to the next, 5 to the third place, and then we sometimes had to make the money up. We would give maybe £1 and a certificate to say that they'd taken part in the Walker Prize for Engineering. And to this day, 2020, the Walker Prize is still presented every year to primary pupils in his old school. Next slide, please, Emma. There we are. A big thank you to all. My friends and colleagues in Hong Kong. Clement, many thanks. This has been put together in conjunction with the staff and members of the Institution of Mechanical Engineers. The Williamson family, over the years, presented with family papers my friends and staff members and students at the University of Edinburgh, my own family, because I couldn't do any of this without them. And finally, and this came at the selection of Alison, who's been helping me at the IMechE, why don't you thank the examiners who failed Theo Williamson? Because if they had not failed him, who knows whether these achievements would ever have come about. In the last 2 weeks, we've been remembering here in the UK an anniversary from the World War. And that final comment came from the British Prime Minister, Winston Churchill. Failure is not fatal. Thank you.
Thank you very much for that very interesting presentation. If anyone listening has any questions, please do submit them, and we've got time for 1 or 2 questions before we draw the event to a close. Joe, we have received one comment in regards to World Cigarette Company, the termination of Mollins, and how it was such a shame that accounts dominate corporate management and often fail to appreciate engineering.
Well, I must have, I've got divided loyalties here, in that my 2 sons both studied, Andrew did engineering, manufacturing engineering at Durham University, and my son Simon went to mechanical engineering, and they're both in finance now. But in some ways, I think part of the problem was Williamson was off sick. He'd been off sick for many months, and maybe if he had been able to speak with them, he would have been able to persuade them that there was a further group of computer-aided tools that were around the corner. And I think it was the timing. Timing, it can be, it can be awful, or it can be fortuitous. The fact that he wasn't there to defend what he was doing, that the Mollin family had decided to sell their shares at the same time. And I think that was part of the problem. That was part of the problem. But again, look at balance sheets. You look at balance sheets. You see the money going out. I mean, it was a big risk all along that Mollins took in recruiting him, just as Tootle back in the early days had taken a risk. But I don't think we should necessarily blame the accountants. They were looking at they had to perform due diligence. They had to perform due diligence, and they performed it, and they reported back to the board of directors. But it did mean that Mollins did not carry on with that work, and I know actually it really annoyed Williamson. Many years later, he went to a machine tool fair in Chicago after he had left Mollins, after he retired, and he'd seen work that they knew was around the corner being demonstrated. But the other side was that the patents that were taken out paid large sums of money into Mollins for many, many years, but they went back from being they went from being a cigarette machine making factory to manufacturing technology, and then they reverted back to cigarettes, their main business. And there's a lot of traditionalists. A lot of people don't like change. And they didn't like the changes that were coming about, despite the fact that there was a whole team. But it really needed somebody like Williamson to drive it. And I think that's why the decision was made. The accountants, I don't think we should blame accountants, but the decisions were made. I hope that answers the question.
Thank you, Joe. We've received one more. Although STEM is being well encouraged the key is whether the fruits of pursuing STEM subjects are channeled to nurturing to become engineers, not accountants, bankers, etc.
Okay, Eva, the question, as I gather here, could you please just repeat the question?
Yeah, of course. Although STEM is being well encouraged, the key is whether the fruits of pursuing STEM subjects are channeled to nurturing to become engineers, not accountants, bankers. That there's a comment, engineering cannot match these sectors in terms of pay, etc. So thus talents go perhaps to other industries. Do you have any comments on that?
Well, first of all, if I can be, again, I don't think, let me put the thing round the other way, all right? One of my colleagues here in the University of Edinburgh was the Professor of Business Studies here. And my son Andrew was torn between engineering and business studies. And I went to see Professor Lynn Thomas. And I took Andrew to see him, and I said, Andrew's torn between business and doing engineering or science. And Lynn Thomas, his immediate reaction was, go and do the hard science, go and do your engineering, Andrew. Go and do it. And later on, I said to Lynn, I said, for a Professor of Business Studies, that was quite a very direct, immediate response. And he told me, look, he said, my first degree was physics from Oxford University, and I've got a PhD in theoretical physics. He said, but towards the end of my time, I said, I realised, first of all, that what I was doing could be applied to what was known as operational research. And so I said, that's why I made the transaction. And I don't believe that doing engineering or science, it's ever lost. That if you do the STEM subjects, yes, I mean, the main purpose is any country, Hong Kong, every country in the world needs people trained and educated in engineering and science. There's a shortage here. There'll be a shortage in your country as well. But frankly, personally, I don't mind if some of my students, having done STEM subjects, move into other areas, because I don't think that's ever lost. One of my most successful students studied with me, and at the end of it, he went on. He came in to see me one Monday morning, and he said, "How do you deal with a Monday morning, Professor?" I said, "Sebastian, I get on with it. Why don't you get on with it as well?" And he said he's never forgotten this. And what did he do? He's now a barrister. And you can imagine the analytical skills that a barrister needs. Yeah, okay, salaries for accounting, salaries for law. Okay, I think at the end of the day, it becomes job satisfaction. Job satisfaction. There's nothing more creative than doing what Williamson did. You know, finding a solution. And at the end of the day, you know, whether you're getting a wage for or a salary for what you're doing, but are you happy doing that? Do you enjoy doing it? And at the end of the day, a lot of young people will say, well, I quite enjoy doing that. I mean, I still get immense satisfaction when former students get back in touch with me and tell me that they're doing, and even more important, I can't do it this year while I'm the president, but supporting them for membership. So, okay, I do accept that salaries in finance are higher, but I don't think at the end of the day, if it's job satisfaction, I think engineering and science will give you an immensely satisfaction career and enjoy what you're doing.
Thank you very much, Joe. I'll now ask Clement Chong to make some closing remarks.
Yep. This is close to the end of the president's speech. It's really encouraging. I do really enjoy my work as a mechanical engineer, be frank. And thank you for you all joining in. In fact, this is our first webinar done in Hong Kong. We should do more often in new normal nowadays. And thanks again, the President Joe's continued support and encouragement to Hong Kong branch, showing we stay connected and support each other. And thank you. And thank you all that the time and have a good time. Thank you.